Today I want to talk about a very important approximation which we often use in physics, which is known as stationary phase approximation, also known as saddle point approximation. And in the later part of this, I'll also talk about a very interesting puzzle, which we can just uh, evaluate using the same principle, some of the same ideas which we use in stationary phase approximation. Okay. So the basic idea is to evaluate the integral, which is up here, this I, and then we have this limit of large lambda, and then this is the integral. Now this kind of integrals are very often used in physics, because in physics when we write path integrals are of form e to the power I s by h cross, where s is the action and h bar to 0 is the classical limit. When we go to the Euclidean time, then this becomes e to the power minus s by h bar, and the small h is equivalent to large lambda, which we need in the stationary phase approximation. We'll assume that fx has global minima at x equal to 0, such that f prime of x naught is 0. Then we can write this fx as a sum over fx naught plus this term which goes to 0 because of the fact that it is a global minimum, and then you have the second term. So we can approximate fx by fx naught plus this second derivative term. Using this, you can write down the integral in equation 1 as this, where you take the limit x to infinity, sorry, lambda to infinity, and then you have the prefactor, which is fx naught e to the power minus lambda fx naught, and then you have the second term. Now this evaluation of this term up here is very common in physics. This is the standard Gaussian integral, where we have integral like e to the power minus x alpha x squared dx, which is equal to pi by alpha square root. The way to prove this integral is that you can write down this integral twice, one in variable x and one in variable y, and then you can multiply it and you get something like this. And then what you can do is you can just write something like this and then go to polar coordinates and solve it. And you can check that this is the result you get. Okay. So now using this result of the Gaussian integral, we can evaluate I to be this, where we write down the limit lambda to infinity, and then we have this nice expression. Now we can make this more precise by adding higher order terms like this, which depends on how much, how precise you want to be. So this is the evaluation of the stationary phase integral in physics. Now there's a problem or a puzzle I want to discuss, which appeared in this CSIR UGC exam, which is usually conducted in India twice a year for the qualification or eligibility test as assistant professors. There was a question in 2012, which was, which of the following is greater, e to the power pi or pi to the power e? There exists many ways to prove this, but I think the most elegant is by writing the exponential as a power series like this. And then if we have x much less than 1, we can ignore the higher order terms and then say that e to the power x is greater than 1 plus x. Right? So this holds if x is small. Now we just put x equals to pi by e minus 1. So pi by e minus 1 is actually less than 1, which we can check roughly by writing pi as 3.14 by 2.7, approximate value of e minus 1. So this is much less than 1. If we put x equal to pi by e minus 1, we get something like this, which when we solve, we get that e to the power pi is greater. So this is very interesting application. Thank you.